All right, so this is the review, the final review for image processing and computer vision. And this is, again, not a comprehensive review of the course, but rather an overview of the second part of the course, okay? Now, the final exam is comprehensive. That means that everything that we have seen since day one to today is included in the final exam. Now, obviously, the final exam emphasizes the second part of the course more than the first part, but there are going to be questions about both parts, okay? So we spent most of the first part of the course talking about geometry, and on the second part, we started talking about radiometry, the study of light, right? So make sure that you review all these different things, and especially the different types of illuminations and shadings that you can get and the shading models that we have covered, right? So remember that this is probably the most important plot here, that you have a light source, right? And most of the time we have assumed this is a point source at infinity, right? And then there is an object, and then there is a vector that indicates the location and the intensity of that light source. There's a normal vector to the point on the surface that determines the shape of that object, and then there is a camera with its camera model that takes a picture of that object under this illumination condition and this orientation, right? We have defined the radiometry properties, or the different concepts like radiance, irradiance, and so on that we have defined based on this model of the hemisphere. The hemisphere of directions, remember, indicates every possible incoming and outgoing direction of light for every possible point on the surface of an object, okay? With that, we identified or we defined what a solid angle is. Make sure that you understand solid angles because they are essential to understanding every other concept that we introduce in radiometry. This is one of the most important concepts to understand, not the easiest one, I know. With that, we define radiance, right, as the power traveling at some point in a specific direction per unit area perpendicular to direction of travel per unit solid angle, right? Sure that you know these things and you understand. Irradiance, the power per unit area not foreshortened. Remember, foreshortening is the angle of the light source with respect to the normal vector of that surface. The Brdf, or bidirectional reflectance distribution function, make sure that you review this. This is the ratio between the incoming and outgoing direction, right? So how much of the incoming radiance is actually absorbed and how much is actually sent back, including the foreshortening that it's indicated here by this cosine, right, that you have. Now the Brdf, typically you have this in the slides. You will see in the literature that it's drawn like this, that it's plotted like this, with a hemisphere, right? And that hemisphere actually indicates the different ways the reflectance function interacts with or defines the shading of the object, right? These are color. Here in this course, we have only seen the black and white or grayscale equivalent of that, right? But if you apply this for R, G, and B, as we saw in the color lectures, then you can get this colorful balls, right, of the Brdf for the three different channels. Radiosity, we have used this a lot because this simplifies our modeling quite a bit. Remember, that's a total power leaving a point on the surface per unit area on the surface, okay? Given by this equation, I integrate or I sum over, right, all the differentials of the outgoing radiance. Radiosity and constant radiance. Remember that we talked about this. The albedo, which is a simplified Brdf, right? So we actually talk about the directional hemisphere reflectance, and then we also talked about the albedo, right? Under all the assumptions that we have made. And make sure that you remember all these assumptions, right? That you have to make in order to go from a Brdf to an albedo, right? And why you can make those assumptions, or rather, when can you make those assumptions and when you cannot make those assumptions, okay? Sources, remember, are considered different than objects because they actually generate energy internally. Objects do not. Objects can only absorb energy. Then we have defined the point sources, right? There are the point sources, very important to understand. They can be very large, but they're very far away, and therefore they're considered points. That allowed us to define the radiosity based on the point source, which allow us to define this standard model, right, of shading. That is the model that you have to remember for shading models, right? And that model includes the albedo, that is the shading, right, times the normal, that is the shape of the object, times the source, right, the vector that determines where the source is and its intensity, right? Okay. With that, we defined photometric stereo. And with photometric stereo, if you have multiple light sources, every time you turn on one of the lights and you turn off all the other ones, and then you take pictures of that, you get an idea of how light refracts back from this surface. And from that, we showed that we can compute both the shading, right, the albedo of the object, and the shape of the object, right? So make sure that you review this, because this is one of the most fundamental algorithms that we saw in the second part. So here's an example with these shading balls, hemispheres that we've discussed. Remember also that we used orthographic projection in our photometric stereo algorithm. You could have used any other fine model, camera model that we have defined, but we decided to use the orthographic. But make sure that you understand why we used orthographic and what happened if we had not used orthographic, okay? What differences would that entail? And then we had this final trick to eliminate shadows or occlusions, right? These are examples. So this is a synthetic example with computer graphics of views of a synthetic object. This is the albedo that's recovered with this algorithm, and this is the shape that's recovered with this algorithm, the normals and the shape, okay? And this is a real object. This is actual data. So we took a ball, we took pictures of the ball under different illuminations, and with photometric stereo, we're able to reconstruct the ball in 3D and its shading model, right? Its albedo. And this is from somewhere, some publication out there where someone used this idea to recover the 3D shape of a more complex object. Now remember convex versus concave and the problems with that. This is important to understand what the limitations are in order to answer all the questions correctly in the exam. Illumination cone, right? We showed how to define an image of an object as a vector in p-dimensional space, where p is the number of pixels. And then from here, we showed that all the images under all possible illumination conditions defined a three-dimensional cone, right? This is the two-dimensional example that I draw on the board. This is another two-dimensional example. The cone is actually 3D, right? But you get an idea. We cannot draw three-dimensional cones, but you get an idea what the cone looks like, and that cone, the points in that cone actually define all the possible images of that object under all possible illumination conditions, okay? And if I do a linear combination of two of these points, I get an image under a combination of two different illuminations, okay? From that, you can also recover, since you can recover the albedo, you can recover the 3D shape with the same equations of photometric stereo, right? So make sure that you review all these things. Then we talk about image alignment, point correspondences, because in the first part of the course, we spent a lot of time talking about point correspondences, but we never said how we're going to find these point correspondences. Well, that's how. Either optical flow, and we spend quite a bit of time defining what optical flow is. Optical flow is not the same as the motion field, so make sure that you understand motion field is the actual 2D projection of a 3D motion, whereas the optical flow is the apparent motion of the brightness patterns. This is, of course, different than the 3D motion as well, but under some basic, very, very simplistic assumptions, then we could define this basic model of optical flow that allows us to find point correspondences by assuming that the brightness or shading of a pixel does not change after that pixel has been translated to another part of the image, right, after a small period of time. We derive this using Taylor to linearize these equations and then use basic methods of nonlinear least squares to find the solution. Okay. Discrete case, limitations. Remember, there is a fundamental limitation in optical flow also, which is the aperture problem, which is that if we look at the small window, then our conditions are satisfied, right, our assumptions, and then we can apply this algorithm. But if the window is too small, then we don't see the whole motion, and therefore we're missing. We're actually computing something that is absurd. That just doesn't make any sense. And that allows us, or that led us to define robust statistical methods to solve this problem. Specifically, we spent some time talking about norms and different types of functions that we can use to robustify these algorithms. We also talk about the illumination changes. We also spend some time talking about how to evaluate these methods, make sure that you know how to evaluate these methods, right? And there are, for example, for optical flow, we talk about two things that are important. One is the magnitude. Are you getting the magnitude? That means how far away the point of the object has moved from image to image versus the orientation of that motion, right? So you have the angle and the velocity. So make sure that you understand these two different things. In your slides, I haven't included them all here, obviously, for this review, but in your slides, you have plenty of examples. This is mostly being used right now for self-driving cars, algorithms like this. I mean, more sophisticated versions, obviously, of these to track pedestrians, bicyclists, other cars, and so on. So something that I didn't cover in class, I want to make clear that not all motion is actual motion or perceived motion, right? So here you have a visual illusion, right? This object seems to move, right? There is actually nothing moving. But the reason this happens is because of something that, on the way that our visual system describes this in the Fourier domain. And there's a lot of literature on that. If anyone is interested, email me after the course is over, and I'll send you links to that literature. But there are many other methods to work to detect motion. Then we started defining more sophisticated algorithms for finding point correspondences, and in particular, we talk about template matching. Remember, template matching is that you have a small window of an image, and you try to find where that window is in another image. Okay? So image A, take a window, and look for that window on image B, right? So that's template matching, and we introduce the very basic notation, which is the optical flow notation that we had introduced earlier, and then we expanded this a little further with more sophisticated methods. And that led us to a definition of the compositional algorithm, which is a way to compute this computationally more expensive algorithms or more complex algorithms in a computational or a more accessible, computationally speaking, more accessible way, right? Less computationally expensive. And after that, we also talk about RANSAC. Remember this random sample consensus algorithm, which allows us to eliminate outliers, because when we're finding these point correspondences, we're making a lot of errors. And we just want to find the model that fits these errors. And RANSAC, for example, if you're looking for a linear model, you're going to find this linear model that identifies these points that define the line and eliminate all the points that are outliers that do not define the line, right? So make sure that you review this. And here's an example of finding point correspondences with the algorithms that we've introduced plus RANSAC. Okay? More examples. Okay. Then we also talk about a finite structure for motion again, right? We had talked a lot about the structure for motion in the first part of the course. Here we revisited with the new tools that we had, and we defined specifically this column space fitting algorithm, which is, in my view, one of the best, if not the algorithm that you should be using if you use a structure from motion, which simplifies the notation that we had defined previously in a way that makes it work much better. And remember that it uses this so-called reconstruction criterion, which is nothing else than the least squares criterion, right? Most of the time when you hear people in computer vision and image processing talk about the reconstruction laws or the reconstruction criterion, what they mean is the least squares criterion. Okay? All right, so you have all the derivations that we gave in class, right? How you compute the derivatives, and then how you solve these equations with nonlinear least squares. And here's a summary of the algorithm, some results. This is an object, a plastic object, right? A dinosaur. Really good, spectacular design here. Game of Thrones kind of. And it's on a rotating table, and it rotates around, right? And then you find point correspondences with the algorithms that we have introduced, and you eliminate outliers with ransack, and you end up with all these point correspondences, and these circles here define the rotation of the dinosaur in that turning table, right? So you can see that that's actually correct. If you don't eliminate outliers, then you end up with something like this, which is obviously incorrect. Okay? All right. Rendering, how you can render things in 3D. We've briefly touched on this. And then we extended we extended the structure for motion to non-rigid structure for motion by defining a shape-based model. So remember, the structure for motion algorithm is given by the simple equation W equals ms. That means your data matrix is equal to the motion matrix and the shape matrix, right? The motion matrix is nothing else than the camera models, and the shape matrix is the shape of the object. And for non-rigid structure for motion, we have to add a shape space that allows us to identify the coefficients of those basis vectors, right? Those basis shapes, that allows us to describe these shape transformations in a small number of shape bases, right? And we show specifically that you can use the DCT basis to do so and find models that are very simplistic, right? So for example, this is a model of a face. You can reconstruct the face in 3D as it was shown here. This is a reconstruction from a video sequence. And then the shape-based model only uses 2 coefficients in that case, right? So it's a very compact shape-based model. That's what we're looking for. We have many more examples in the slides and in the papers in Canvas. Before we talk about this, obviously we had to introduce Hilbert spaces. So make sure that you review everything that we cover about Hilbert spaces, because that is fundamental for everything that we have done in that second part of the course, right? The Hilbert space is a real or complex inner product space. There is also a complete metric space with respect to the distance function induced by the inner product. It follows certain properties that we spend quite some time defining. After defining the Hilbert space, we define functional spaces. And specifically in functional spaces, we use the Fourier series. So make sure that you review functional spaces, because now a function can be defined as a vector of coefficients, where these coefficients are the coefficients of the basis functions that you use. And the basis functions are whatever basis function, complete basis function you want to use. For example, the Fourier bases, right? And that's what I want you to review. And remember, these are the cosine and sines that we have defined, or the exponential of negative I, right? Which allows us to define all the different rotations and all the different functions. And here you can see, for example, this line can be approximated with a combination of sines and cosines, right? We also talk about the Fourier transform. Make sure you review the Fourier transform, because that is very important, especially for linear filters, right? So we spend some time talking about linear filters, how these are defined by convolutions. You have also had some homework on understanding how a convolution in the real domain corresponds to a product in the Fourier domain, right? So if you take the Fourier transform of your image and your filter, then you multiply them in the Fourier domain, and then you do the inverse of the Fourier transform, then that's the same as doing a convolution, right? So make sure that you understand all these different concepts. Then we talk about the obviously the discrete Fourier transform, and within the discrete Fourier transform, we define the DCT basis, the cosine transform, because it's a complete set. And with that, we define compression algorithms. We use the DCT both for non-rigid structural motion and here for compression algorithms. And basically, we talk about JPEG, which is one of your homework as well, right? And here's some examples of that. We then, at the very end, briefly talked about the projective space and projective transformations. Now, we only covered the surface of this, not even the surface, right? We went tangentially to the surface of what the projective space and projective transformations are, but at least we cover some concepts that I hope are going to be useful for you to understand whatever you may want to read after this course, or if you want to take the computer vision course after that, okay? So these are some of the drawings that you have in your slides in Canvas that are things I was trying to draw on the board, but because I'm not a very fancy or professional artist, I'm not able to do these beautiful things, but you have these things online. We talk about quaternions. Now, I didn't talk about this notation of quaternions, right? This is just one notation. We talk mostly about this one, right? Where you can describe the vector as a direction, v, and a scalar s. You could also describe quaternions as these 4 different elements, these 4 different coefficients. And in that case, you consider quaternions as an extension of the complex numbers. And now here, I, j, and k are, if you take the square of this, are the square roots of -1, so you get -1. And then you also have these equalities that hold here, and that defines just this 4-dimensional space where quaternions are defined, and that's why they are called quaternions, right? And this is the definition of the product, right? That somehow I managed not to explain very well this time around on the board. And then finally, the very last topic was color perception. And we covered a variety of important, very important points and topics in color. We talk about the spectrum, right? Color does not exist. Color is an illusion. What exists is an electromagnetic wave in the world, and that there's a small band in that electromagnetic wave that we call the visual spectrum that we assign colors to, right? Depending on its frequency, right? Its wavelength, rather. And the visual spectrum that we see can be defined by the hue, which is what we have typically called color, the saturation that goes in and out of that cone, and the intensity or brightness that goes up and down, okay? The retina and our cameras, so both the human eye and our cameras have 3 different types of sensors. Now in the retina, you have the S cone, M cone, and L cone. And in cameras, you have the RGB usually sensors, okay? They're sensitive to RG and B colors, red, green, and blue. They're not identical to one another. Actually, it's quite different, but most people just assume that they are, okay? But they're not. I want you to understand that they are not the same. We talk about opponent colors and how to compute opponent colors. These are important because we believe that that's what the human visual system is based on. So if you want to design systems that work like the human eye, or that are pleasant to the human eye, or that people can look at and understand, then you should be using models that are based on the human visual system. I also talk about isoluminant color. That means the color that is defined when you remove the shading information, or so-called luminance, of that RGB image. That gives you the shading and the 2-dimensional color space. So the opponent colors is one example. You could have 3 channels, one that defines the luminance. Here on the left-hand side, right, it would be this one right here. And then the 2 color channels that could be, for example, the red, green, and the blue, yellow, right? So as we saw, if you have, this is fundamental from what we saw in our last lecture, right? If you take a color image like this and you compute the luminance, that is the luminance, that's where the shading is, right? And the 2 opponent colors, these are orthogonal to the luminance, are these two images here, right? Now, if I convert these 3 images to black and white, what's going to happen? The top one is going to remain exactly the same because it's luminance. but the other ones have absolutely zero luminance, so you see nothing, right? There's nothing. There's no shading in those images. There's only color. I want you to understand this. We also talk about what happens with opponent colors when you use them on signs. So remember the importance of the additive and the multiplicative or subtractive models of color vision. While yellow is important that we talked about, here's a model of the additive color mixtures, and here's the subtractive color mixtures. Okay, so make sure that you understand the difference between these two models, because that's important. And also, as I said, that you understand the independence of color and shape, meaning the shape of the object that creates the shading. Okay, all right, that should be it. Good luck at the final exam.